In SAC 105, problem number 4, we've got a board with a disk under it. Let's see if I can get a reasonable sketch of that. I can call it a before and after picture. There's the board. Here's a disk attached to it. Give that a little 3D-ness. And we got this massless rod up here, and the whole thing's spinning about that axis with some omega. Then the disk drops off, and the question is, how fast is the board spinning after that? You got to be careful to write omega here, as there is a W given in the problem. I don't think that's going to be of any use to us, but we don't want to confuse the symbols. Alright, so that'll be the before picture. This will be my after picture. The after picture, the disk has dropped off. So it'll be down here someplace. I'm going to assume it's still spinning. And in fact, there's been no torque exerted on the disk from the before and after picture. So it'll be spinning at the same rate that it was. And it just fell off. So there's actually no change to any angular velocity. That is, the angular momentum of the disk didn't change. Its moment of inertia didn't change. So however fast it was spinning, it's still spinning. And that goes for the board as well, separately. So actually, they're asking for omega, how fast the board is spinning afterwards. But that's the same as the original omega. So the problem really boils down to what's the original omega. I call this before and after. We've essentially solved the important part of it, that the omega doesn't change. So whatever it was before, that's what it is now. I'll express the total momentum, and I'll go, what's that? Counterclockwise is viewed from above. The same kind of curvy arrow that I got there. Counterclockwise is viewed from above will be the sum of the individual momenta. Counterclockwise is viewed from above. And that's just, I call it LB plus LD, the board and the disk. And I believe they gave us the moments of inertia. So I sub B is the moment of inertia of the board, and I sub D the moment of inertia of the disk. We're calling the total angular momentum of the combo object is L, so that the total angular momentum is just L, and that's given as IB times omega plus ID times omega. So moment of inertia of the board times how fast it's spinning plus the moment of inertia of the disk times how fast it's spinning. And it doesn't matter whether we're looking at the before or after picture. It's the same in both cases. Okay, I'll factor out the omega. Since that's what I'm solving for. Then I'll divide both sides by this sum of moments of inertia and switch sides at the same time. I'm supposed to get what I'm solving for on the left, and that works out. Plus I sub D. So this problem represents a good example of the fact that some problems are easy. if we're always applying conservation of angular momentum, starting out with the same way every time, we've got to recognize not all problems fall into that category. It's true, angular momentum is conserved, but we didn't have to write, the sum of the momenta in the before picture is equal to the sum of the momenta in the after picture, because angular momenta, I'm talking angular momenta, because it's clear there were no torques even exerted by objects on each other in this problem. So it turned out to be a pretty simple problem. It's just a matter of figuring out how fast it was spinning in the first place based on the given information. And that does it for SAC 105 problem number